here just to make sure that they have the same number of counts. So if you look at your images and draw regions of interest, you should be within plus or minus 5% of the number of counts as you move around your gamma camera. Let me just see if we... Okay, let me just get to the... do any of you guys seen this camera? So I think it's a GE. I want to take a look at, here's our spec though. Looking at this picture here, okay, this is a 64 by, well, maybe it's 128 by 128, but notice how grainy the image is. And then over here, your whole body images, notice that it's 1024 by 256 crossways. Most people do much higher resolution than that. That's kind of an old one there. What is important though is the number of counts that you acquire. Remember, we said that for whole body images, you need at least 1 million counts. So you have to make sure that your imaging system moves slow enough for that.
Sir Aki, do we have that handout?
No, I'm going to send it to you. I just came across it when I was there. This is another thing that we were talking about, reconstruction. Okay, this is filtered back projection. I just got this backwards up here. Does everyone know what the difference is between iterative and what iterative reconstruction is? Have you heard that term? What does it mean?
It's what we use, but what is it?
Probably the best definition of iteration means a guess. And let me just kind of give you a quick overview on that. Let's say that we took a picture of a patient and we have a 3 by 3 matrix. The computer acquired, we had 1, 2, 3, 4, 5 through 9 counts detected in each box. Okay? So in other words, each one of these boxes has a certain number of counts in it, and it's up to us to figure out where those numbers go. Now I will tell you that when the camera was measuring, it detected 15 counts here, 15 counts here, 15 counts here, 15 here. So all the way around the patient we got 15 counts, both on the horizontal and the diagonal orientation. So, have you guys ever done this before? This is a good old math problem here. Okay, so we know that there's a maximum of 15 counts in here, and we know that these were the numbers that were collected from the various positions. So your job is to put these 9 numbers in the boxes here to where they add up to 15 regardless of what direction you go in. So iterative reconstruction technique, this is what the computer is doing. Okay, except obviously you're going to have different numbers on the outside here, but you, or the computer, has to guess what those numbers are. I will give you a hint. Okay, 5 is in the center here. Does that help? Huh? Doesn't help?
Yeah. Look at it.
Doesn't this, you guys never like to do math problems, huh? Okay, well, let's try this. 4 and 5 are 9,
6.
and 6 is 15, okay? Let's do 8 and 5 are 13, and 2 is 15. Okay, can you guys figure out what the rest of the numbers are now?
9.
Huh? What should I put here?
9.
9 here, what here?
1.
1, okay, what about up here?
3.
Okay, that wasn't so hard, was it? Now, just imagine if you had 16,000 of those to guess. Okay, well anyway, each time you make a guess, that's one iteration. So let's just say you put the numbers in here and you found out that they didn't add up properly. Okay, that would be one attempt. So then the computer, if it does find areas where it does add up to 15, it'll leave that there, and then it will try a second attempt. So in other words, it keeps on trying and putting numbers in boxes until things get as close to 15 as possible. That's why you tell the computer how many iterations you want it to attempt before you give up on it. Okay? If I would have given you this, and if I would have given you the number 5 in the middle, it probably would have taken you some time. If I said, okay, we're not going home until this iterative box is taken care of. Okay? So now you understand the difference between iteration and back projection? Back projection, we would have 15, but the computer would say, okay, 15, 15, 15. Over here we have 15, so 15, 15, 15. Here we have 15, 15, and 15. So in all the... Okay. Oops. Too much here. Okay, so with back projection, then we would know that this one here is going to get a large number, but when I subtract 15 from the whole matrix, the only one that's going to have anything left will be this, right? Okay. What I'm trying to find here, and I haven't seen this stuff here, is that this is what we are typically using now. So the filtered back projection image is very grainy. Okay, this is the iterative reconstruction. And there's different, they have like OSEM, and they have different names for it. There's algebraic, iterative reconstruction techniques, but they're all basically just variations of what we just did. You know, there's a little bit more complex math involved, but normally you get a picture that doesn't look so grainy. Okay, can you guys see the difference there with that? Okay. What I'm looking for is gamma camera spec quality control. The uniformity, okay, can you guys see this bullseye ring? Okay, this is a common question that you'll see on your nuclear medicine board exams. If you see that ring artifact, it's because the gamma camera is no longer uniform. Okay, so there's variations. As the thing rotates around, that uniformity error stays in the same place, and that's why you get a ring artifact. Normally it's a lot more dramatic. If I had just a flood here, it would be much more dramatic. But basically it's like it's a ring that goes completely around here. And that's typically seen with a that type of an artifact. Okay. So the way that you correct it, this is where you do your 30 million count or your 120 million count flood. And again, it's because you want 1% error in your images. So if you remember, that's 90,000 counts per pixel, right? So 90,000 times 4,096. Actually, if you calculate the area of this circle here, if you had 4,096 pixels, and that would be as if you had a perfect square, but since you have a round circle, we have to decrease the number of counts, or the number of pixels. So you really don't have 4,096 pixels here. You have something much less because the areas out here don't have anything in them. Okay? But like I said, you normally would be there all day doing that. Okay? And again, normally on your gamma camera, you should do uniformity floods on that also. And I told you that if you do have a camera that you do uniformity correction on, then you need to take a picture with it on and off, so you can actually see what your crystal looks like. Right? That's what Mr. Radke says. Okay. Now, the other thing that most people don't tell you, and again, I'm not stressing this because most people don't do it, but people actually have uniformity floods for all of the radionuclides that they use. So they'll have a uniformity correction for indium, one for iodine 123, one for iodine 131, one for thallium. So every radiopharmaceutical that you use, they have a correction flood for that. Why do you think they do that? Because it gives us something to do, right? Makes us look important. Let me ask you this. Do you think that each radiopharmaceutical is absorbed the same in the crystal? Nobody's shaking their head yes, so you're absolutely correct. So remember, lower energy photons are pretty much all absorbed in the crystal. As the energy increases, then the number of photons getting absorbed starts going down, because some of them are going to pass through and either deposit no energy or only deposit a partial amount of energy. So that's why you have the pulse height analyzer that rejects them. Okay? And like with I-131, only about, I think we lose about 20% of the photons that are generated from it. Okay. I'm not going to, this is not one of the things I was looking at here, but let's say that I had a radiopharmaceutical that had 2 energy peaks. Just ignore the stuff on the left here for a minute. What do you think would happen if you saw this? Let's say that you do a picture of indium. Here's camera 1 and here's camera 2, or here's head 1 and head 2. What would this tell you?
Contamination of thallium?
Well, we're assuming that notice, this technologist who did this flood source was very concerned about contamination, so they have a polyvinyl towel or a chuck protecting the collimator. So we're going to assume that it's not the flood, or we're going to assume it's not the source. But what does it mean when you see 2 dots when there's only one source? This one is okay, there's no problem with this. Okay, let's say that I have 2 pulse height analyzers turned on, because what's the energy of indium?
247.
Okay, 173 and 247. So that means that in this image here, both peaks are superimposed on each other. So what happened here then? No, it's not diverging. Huh?
The pulse height analyzer is broken on that one, where it's making it look like it's coming from 2 different areas when it should be superimposed.
Okay, now, so would that be the pulse height analyzer? This is what Monica said, and she's on the right track. Okay, she's saying that the pulse height analyzer is broken, and that's why we get 2 dots there. Ashley, what would be your interpretation of this?
No idea.
Mr. Singh?
Maybe the pulse shaper?
Not the pulse shaper. Okay, you have a ratio circuit, right? ratio circuit is what determines the
Oh, yeah.
position. Okay? When you turn on more than one window, you're turning on more than one ratio circuit. So each window, so like in most gamma cameras, you have a maximum of 3 energies that you can image. Each time you turn on one of those, that's a whole separate circuit. It's like you've got 3 different gamma cameras. So what's happening here is this is that multiple window registration problem. Okay? One pulse height analyzer and ratio circuit is putting it out here, the other one is putting it here. So this might be the 174, and this might be the 173, that might be the 247. They're not being put on top of each other, they're not being superimposed. This is an X and Y gain problem. Okay? How would I know that? Well, it would look like all my images had ghosts. There'd be like something on the outside of it. Or I'd get like a double exposure. Okay? If I wasn't paying attention to stuff like that, then this is an issue. What they need to do is adjust the ratio circuit and the X and the Y gain. In this case here, because it's in the vertical orientation, this is a Y gain problem. And one of the ways that I could prove it, what would be a good way to prove that, other than doing this test? Mr. Viet, I don't bother Mr. Viet and Mr. Gregg enough, so. What would be a way that I could prove that I have X and Y gain problems with that? I'm waiting, I'm your boss.
Use another radioisotope with 2 different peaks, and if it's the same thing, then
Well, I'm going to give you a quicker way than that.
You could
Okay.
turn off
what you
the
do?
pulse height selector to select only one and then do it to.
Okay, well, I still have the same problem, but, okay.
What are the interesting?
Okay, what were you saying?
The bars help?
Yeah, what would I look for on the bars?
Is it's their
Wrong numbers.
Yeah.
Wrong numbers.
Right, if I count the number of bars, I should have the same number of bars in the X and the Y orientation. Remember, you're supposed to every day turn that thing 90 degrees. You know, you're actually supposed to take 4 images of this. If I count the number of bars, I should have the same number of bars in each direction that this thing rotates. So, in this case here, when I turn it to the Y, if I rotate that at 90 degrees, then this one here, I'm not going to have the same number of bars, I'm going to have less. Okay, because it's my Y, my Y position that's a problem.
I was thinking for a specific exam in my head. I was going over all exams in my head to see that that's what the...
Yeah. Well, I'm just, you know, I know that you probably feel like you're getting too much information, but, you know, when you're out there in the real world, hey, you're on your own. So the only informative sources you're going to have are the textbooks that you bring with you. You know, my daughter has her collection of nuclear medicine books at work, and believe me, problems come up all the time. Okay? So the thing is, you need to establish a good resource. You know, so if you do have a problem, I mean, if I can answer a question for you, I'd be more than happy to. The thing is, you know, you're on your own. Most nuclear medicine departments are going to be one-person things. Yeah. Huh?
Really?
Yeah. You're going to be lucky if you have. I mean, over at like Kaiser Sunset, they've got, I don't know, they maybe have 3 or 4 techs for like 8 different cameras.
Jeez.
Yeah.
It's spoiled
Okay.
that. You don't know that.
Yeah.
It's
Well,
a
they.
checker room.
Yeah, I know. Most places you aren't that lucky. You get 2 rooms. Okay. Linearity problem. Remember we talked about the straightness of the lines. And so now we're going to talk a little bit about going back to our spec here. I'll send this to you. This actually is pretty good. I just came across it when I was. Okay, the pixel, well, the uniformity, the first thing when they talk about pixel deviation, not all of your gamma cameras have this, but basically any pixels that have more than plus or minus 5% will be highlighted. You know what I mean by that? Okay, let's just say here's your uniformity thing. If the gamma camera detects pixels that have 5% less than the average, it usually assigns them a white color. If it has more than 5% than the average, it'll make it black. So basically it kind of gives you a map that shows you the number of counts in each pixel, and because with SPECT we are only allowed a 1% variation, 5% is considered too much. So it's like a road map. So you'll see these areas, you'll see pixels that are off, highlighted in either white or black, or sometimes they'll just give you a report. You know, they'll say that you have 16,384 pixels because you did a 128 by 128 matrix and you accumulated 120 million counts. Okay? And it will say that, you know, 100 have less than 5% and 100 have more than 5%. So it'll give you a breakdown in the number of pixels that were detected to be out of range. Okay. As I said, either you have not seen this or they haven't done this, but please believe me that it exists. Okay?
It's actually funny, we talked about gamma camera last week. And,
Yeah.
Me and Greg saw the PM doing
Really?
Yeah.
Lost a PM to.
it.
Well, it was a wire.
It was
like a-
technically the water
But
connector.
it was kind of cool.
Well, you know, and sometimes one of the things that, you know, this, we talk about integral and differential uniformity. I don't care about this formula here. This is the formula for it. But remember we said, what is the difference between integral and differential uniformity? Says those 5 pixels in the central field of view are located. The largest difference in those pixels are then found in whole sets. So the integral uniformity, we looked at the entire crystal, and it's going to detect the one that has the largest number of counts, and the one that has the lowest number of counts. It could be anywhere in the entire useful field of view. The differential, it's only going to look at groups of pixels that are together in the central field of view. Okay? And normally, like I said, the integral and differential uniformity mainly apply to SPECT imaging. We don't traditionally do this with just regular uniformity. Okay? With regular uniformity, all I want to make sure of is that if I do have a uniformity computer, it's not correcting more than 10%. Okay? But otherwise, if I do SPECT imaging, then I should have somewhere in my quality control my integral and differential uniformity. Okay, going over to the next page. This corrected matrix, again, this is something that you don't have to worry about. But this kind of goes back to that thing where I was telling you where we highlight pixels that have more than 1% range variation. So it says this summarizes the number of pixels with correction factors of 2, which means they're 5% too much, and pixels that have correction factors of less than 5. So in other words, this is looking at the output from your uniformity correction computer to find out which pixels are being, you know, overcorrected or undercorrected. So on this one here, if you have an area of your gamma camera where the number of counts is twice as high as the surrounding pixels, they're going to multiply it by a factor of 5 to bring it back within range of the other surrounding pixels. You with me on that? The correction matrix, okay, we have one that just shows us the pixels without any correction. Okay. On this one here, okay, let's say that we have an area where the number of counts is 2 times higher than all the rest of the surrounding area. So the corrective matrix would tell you that this group of pixels here is being multiplied by a factor of 0.5 to lower their counts to where they're more in line with what the rest of the camera is seeing. So in other words, if everywhere around here we have 1,000 counts in all of our pixels, for some reason over in this area they're getting 2,000 counts. Okay? So the uniformity computer is going to say, okay, we need to lower the number of counts here. And it's going to multiply all of these pixels here by this corrective factor so that they're in line with what the rest of the camera is seeing. Yahoo? Okay? And then on the other hand, over here, let's say we have an area where there's only 500 counts being detected. So the correction on that to bring it up to 1,000 is going to be 2 times. So all of the pixels that are being corrected by a factor of 2 or decreased by a factor of 0.5, those will be identified. Okay? And that's why they call it a correction matrix. But, as I said, I don't normally see cameras doing this too much anymore. I haven't seen this. If they do it, they're probably doing it internally. And if you wanted a display, then that would be something you would do. But coming down over here, okay, before I told you that the uniformity was done daily, now I would say that for spec uniformity, it's probably done at the most maybe once a week. Some places probably maybe once a month. Okay? I don't feel comfortable with that. In my day, they told us anytime you do spec, you have to have a uniformity flood for that day. But, you know, like I said, it's changed. The stability of cameras is better than it was. So you need to either contact your manufacturer, or you need to just set up a policy of, okay, every week we're going to do a 120 million count flood on Friday night when we leave. Okay, that way it'll accumulate over the weekend, and on Monday you should be ready to go. Okay. Center of rotation. How many of you guys do center of rotation? How many of you have seen a center of rotation? You think so?
That one, there's those 3 points in space and it goes around.
Yeah. Well, actually, all you really need is 1 point in space. And so tell me about it. Okay, you just graduated from Loma Linda University. You are a nuclear medicine technologist. You got a job over at John's Imaging Center and Bar. Spa, okay? So you're going to come work for me. And because I know you're a Loma Linda graduate, I'm going to give you $50,000 a week. So,
I'm sorry, right now?
I'm going to give you $50,000 a week. Okay, so tell me about center of rotation. You guys do it every week?
Yeah.
When do you do it?
Every Monday morning.
I want you to hear this, guys, because, oh, we don't do it at our place. Quarterly, wow. Okay, center rotation should probably be done every week. Okay, and what you typically need, okay, or this is what you're trying to do. Okay, let's say here's your gantry. Here's your detector. Here's your table right in the center And then normally you just put a point source here. Okay? And then you acquire an image 360 degrees. Okay, so what am I trying to prove with this? Because remember, you guys are only a few months away from knowing everything there is to know about nuclear medicine, right? The graduation is in August.
June.
Well, I mean, but you're not actually through. Yeah, you guys get to walk the walk and talk the talk, but you guys aren't free and clear till till August. Okay, so we're looking at February, so March, April, May,
6
June,
more
July,
months.
August. So you're 6 months away from being an authority in nuclear medicine. Okay, so what are we looking at here? Let's say that we use the 64 by 64 matrix to acquire our spec image.
That point in space is indeed where it is in the image.
Okay, well, I mean, yeah, that's what we're saying is, so you're telling me that regardless of the position, when this thing goes through all 64 positions here, it should be in the center, right?
Mhm.
Okay, if this source is in the center of my gantry, and regardless of where the camera is looking at it, it should be in the center. Okay, so where's the center at if I'm using a 64 by 64 matrix?
Shouldn't it?
Actually, where should it be if it's in the center of every image?
Halfway,
Okay, so what would that be?
32.
Okay, regardless of where you are looking at this thing, okay, remember this is 0 to 64 over here, and 0 to 64 down here. So position 32, that's where my source of radiation should be, regardless of where I'm looking at it from. Okay? Some places will give you a graphic representation. I don't know, for some reason people like graphs. So they'll give you the position 32, and here's 64 up here, and here's 0. They'll have a line that goes across like this. So this will be the projection, and this is projection 1, 2, 3, 4, okay, up to position 64. So these are your projections, and then this is where the position is of the source. Okay? So if you get a nice line that looks like that, that's great. But unfortunately, let me show you a uniformity flood and a center of correction flood here. By the way, how much error am I allowed before I got a problem?
Plus or minus
Just
half
that
a
one
pixel.
percent.
Huh?
So it's plus or minus half a pixel.
Okay, so what's my range then?
32.5 and 31.5.
So that's the 1%.
Okay, normally you're going to get something that looks like this, and then your center of rotation may actually look more like this. Okay? So long as it doesn't exceed that 0.5 pixel, you're okay. But yeah, that's what you're basically looking for, is to determine if that's the issue or not. Oh, come on, John, where the heck is it? Well, after you guys get back from lunch, I'll show you the center rotation. But regardless of what, whatever matrix size you're using, if I'm using 128 by 128, where should my center of rotation be?
14.
Huh?
14.
64.
Oh, 60.
Yeah. The center should be, so this should be 64 plus or minus 0.5. Okay?
When you're doing center rotation, it's absolutely imperative that you have the source dead center between the two heads, right?
Yep. Yeah, and normally you can adjust it by raising or lowering the height of your table, and making sure that it's like right in the center. That's the important thing. If it's not in the center, then you're going to have a problem.
I didn't know you just eyeball it.
No,
It was on
you have your grids, and you also have the table height and things like that. So, I mean, normally it has to be in the center of what we call the field of view. So if you remember that the field of view is what your detector actually sees when it goes around. And remember that, for most of our fields of view, they're typically about 30 centimeters. And some of them are larger. That one of the big problems we had with PET CT was the difference in field of view between a PET detector and a gamma camera, or a CT scanner, I mean. Okay. So the next thing that I have here, other spec quality control, what they call eccentricity. Boy, there's a good one. When you were doing your flood, you probably, like you said, at my hospital, I have a piece of plastic that's exactly a perfect square, and there's a hole in the center. I could put a radiation source in the center, and then I put one in each corner. Okay? And then when I do my flood, now this is for my center of rotation, but these other ones are for what they call eccentricity. What that means is when I go and reconstruct these images, what should I see? Or what am I doing it for? If that's a perfect square, what should the distance be between this pixel and this pixel?
The same as the other.
Exactly. So, on my image, when I reconstruct it, I should have one here, and one here, and then one here and one here, correct? Okay, but what if I have it here and here?
Then it's not right.
There's something wrong with my x and y coordinates.